Here is a detailed classification chart of the standard phonemes in the American English language. So phonemes are classified into vowels, consonants, diphthongs, and semivowels. Vowels are in turn classified into front, mid, and back vowels. So the front vowels include the I, A. So all of these are pronounced when the tongue is brought to the forward position. And mid position of the tongue brings out mid vowels, and when tongue is taken to the back position we hear back vowels such as U, O. Diphthongs are a combination of vowels. When two vowels combine together they are brought out as diphthongs. And there are semi-vowels which do have the characteristics of vowels but not exactly are they having the spectral characteristic of vowels, and so they are called as semi-vowels. They are classified into liquids and glides. Examples of liquids are W, L. Examples of glides are R, Y. And consonants also have a wider classification including nasals, the stops, whispers, fricatives, and affricatives. The nasal sounds are brought out through the nasal cavity. They include M, N, ing, and stop consonants include the voiced and unvoiced. Stop consonants like the BDG on the voice side and the PTK on the unvoiced side. The whisper sounds are also consonants which are brought out by whispering process. And fricatives are high frequency phonic sounds. They are also classified into voiced and unvoiced fricatives. Voiced fricatives include the Z, V, whereas the unvoiced fricatives include F, S, and we have affricatives like the J and C. Talking about the vowels, they are the most interesting class of sounds in the English language. They have good spectral periodic representation, and so the speech recognition systems predominantly rely on the vowel recognition to achieve very high accuracy in their recognition rate. And vowels can be stretched or compressed as much as the user wants. And we see that vowels are classified into front, mid, and back vowels based upon the position of the tongues. And we have diphthongs, which are gliding vowels, gliding monosyllabic vowels. They start from one articulatory position for one vowel and they go to the position of another vowel. For example, A, it starts from A to E. We have boy from O to I. So this is how gliding vowels are pronounced and characterized as diphthongs. Semi-vowels on the other side, they do have some characteristics of vowels, but they are characterized by the gliding transition in the vocal tract area having adjacent phonemes. Examples of semi-vowels include W, L, R, and Y. We do have nasal consonants such as M, N, ing, which are all produced by the glottal excitation when the vocal tract is constricted along the oral passageway. And we see that the velum is lowered for the air to be given way through the nasal cavity. So when the sound is being radiated through the nostrils or the nasal cavity, we get the nasal consonants. Next are the fricatives, the phonemes that lie in a very high frequency region, even to the order of um, thousands of hertz. We go for analysis of voiced and unvoiced fricatives. So the unvoiced fricatives are produced by a relaxed vocal cord. Examples being F, S, sh. So all of these are unvoiced fricatives. So there is some constriction brought near the lips, near the teeth, and at the middle of the vocal tract. Whereas the voiced fricatives are counterparts of the unvoiced fricatives, Examples being we, Z, and all of these are produced by two excitations, one at the vocal tract, vocal cords, and nearby to the vocal cords. So this produces voiced fricatives. So we can see constriction at the vocal tract and some turbulence produced at the neighborhood. This produces voiced fricatives. Next, let's explore about the voiced and unvoiced stops. So the stop consonants B, D, G are voiced stops which are transient, much non-continuant sounds, and they build up pressure. We see that a constriction is produced at the vocal tract and it then releases the pressure. Different stop consonants have constrictions at different articulatory position. B as constriction at the lips, D as constriction at the back of the teeth, and G near the velum. So at some point of time there is constriction, meaning there's no sound that is being transmitted from the lips, after which the sound is released. This leads to production of the stop consonants. And so we are very sure that the stop consonants are much dynamic in nature. They are highly influenced by the vowel that follows the stop consonant. So how I pronounce a stop consonant depends upon the vowel that is ahead of the stop consonant. So we had a thorough study about the articulatory phonetics of speech. Let's explore about the acoustic phonetics. So acoustic phonetics is a field of speech processing that studies the acoustic properties of speech, and we are much bothered about the time domain waveform and the spectral characteristics of speech. We do an acoustic study of speech production system, comparing our speech production system with the wind instruments or the resonating standing waves in the air tube. So this is a half closed tube. We see that at the output the open end is characterized by lips. So the tube is uniform. It's assumed to be uniform, though our vocal tract is not a uniform tube. We assume this acoustic study to be performed on a uniform tube. So there is a change of pressure. The change of pressure is smallest at the open end and highest at the closed end. So we see that P is equal to maximum at the closed end and P is ideally 0 at the open end. So the length of the tube, it speaks about the maximum frequency or pitch that an individual can reach. So the wavelength is characterized by 4L, 4 by 3L, 4 by 5L, or harmonics are followed. It's incidental to know that a typical adult has about 17 centimeters long vocal tract and speed of sound in air or vacuum is 340 meters per second. And to know the frequencies that are pertaining to this wavelength, we follow this relationship of lambda is equal to C by F. So higher frequencies are brought out by shorter wavelength and lower frequencies or lower pitches are brought out by longer wavelength. And this is how we calculate the resonant frequencies. So the first formant or resonant frequency is given by C by lambda 1. It is approximately 500 Hz for a person with a vocal tract length of 17 centimeters. The second formant is brought out as the third odd multiple of F1. So 3 into 500 gives us 1500 Hz. And the third formant is brought out as the fifth multiple of F1 or the first formant. So 5 into 500 gives us 2500 Hz. So for an adult with vocal tract length of about 17 centimeters, we see that the first formant appears at 500 Hz, second formant appears at 1500 Hz, third formant at 2500 Hz. And though we are successfully analyzing our vocal tract by using uniform tube, please note that our human vocal tract is not uniform in nature, and we see that roughly one formant appears every 1 kilohertz practically. The formant frequencies are not harmonically related, but we see that they are displaced according to the shape of the vocal tract. And there are time and space variations of the vocal tract. We call them as nasal coupling, radiation at the lips, the spread of sound in the ambient air, different energy losses, and rotational airflow. So these are some of the shortcomings of the vocal tract which are practically seen, and these are a few of the reasons why a uniform tube model is not an accurate model to emulate the human speech production system or the vocal tract system. So we consider the lossless uniform tube to just have an overall abstract view about the speech production system. So what happens in an uniform lossless tube? There occurs sum of pressure waves moving at the speed of sound in vacuum in the same direction, and wave is prescribed to be planar. And so to bring out the entire structure of the vocal tract, we concatenate different uniform tubes and bring the entire vocal tract as a concatenated uniform tube model. So here is a quick formula for finding the reflection coefficient of the uniform tube model. So we have the reflection coefficient as a function of the cross-sectional area at the nth position and also at the n+1th position, and the reflection coefficient will lie between -1 and +1. So the reflected pressure waves are expressed by this matrix by taking into account the forward reflection coefficient and the backward reflection coefficient, considering the forward moving wave and also the reverse wave. So with this model having concatenated uniform tubes, having the forward going wave and the backward wave both at the nth position and also at the n+1th position, we bring out equations based upon the Kelly-Lochbaum equations to know how much of reflection happens over the speech signal, when it travels through the uniform tube, essentially emulated as the vocal tract. So we can see that f0 of z is given by the original signal x of z plus gain into the reflected signal. So we assume that Bn of z is equal to 0 at the last tube with the index n, and we assume that there's no reflection at all coming into the last tube, which is brought out as lips. G is pertaining to the gain at the glottis. So this is how the forward traveling wave is characterized. It is characterized by y of z is equal to fn of z. And we realize this uniform tube model as a lattice structured model, and it is analyzed using adaptive filtering.